Welcome back to Trunova-AI. Today we will be talking about embeddings in generative AI and how they have become the new indexes. So in traditional systems, we store data and search by the exact value. In SQL, we have all seen those employees table example where we search employees based on salary, based on ID, and but in AI systems, we are storing meaning and search by similarity. The technology that makes this possible is called embeddings, and the system that indexes them is called vector database. So, in this episode, I'll show you why vector database is basically indexes for meaning. And after this video, the SQL engineers will feel right at home, and we can try to relate SQL engineering with AI vector databases, and we will be more confident. So let's get into it. Now, the first thing which we'll be looking at is what is indexes. Okay, so indexes are nothing but we can understand indexes as a data structure that helps you avoid scanning the entire table. And if you have a table, instead of checking every row, you jump directly to what you want. Now imagine you have a table, you have two tables. Let's say this is table 1 and this is table 2. Table 1 has just two rows. Table 2 has, let's say, 2 million rows. You want to scan something on table 1, it will be very quick because it has just two rows. But if you want to scan something in table 2, it will take a lot of time. Now to speed up the responses of queries on tables like this, which has a lot of data, we use indexes. So basically, an index is a tool that will help us search this big table efficiently in very less time as compared to the traditional ways where we go and search the table row by row. So, for example, MySQL uses the index in the background to retrieve data quickly. So we can understand indexes in MySQL is like let me give you an analogy. So you have seen books, right? So in books, we see there are indexes at the end of the books, and indexes at the end of the book has terms and the pages where the term can be found, which helps the reader like quickly locate the page that references a term. So if you want to find a term, you go to the indexes at the back of the book and we find on which page number that term is located. So we directly jump on that page number instead of going page by page. So this is the analogy and logic behind using indexes. Right. So there are certain examples of indexes which we use. For example, we have B trees for range queries, and like it's balanced trees. So the if you want to when we solve data structure question and we understand how binary trees, balanced trees work. So if you want to search a number, it's not we perform that in log n time complexity instead of order of n. So basically for faster search, we use balanced trees. So the time complexity of this search is basically log n. Then we have some indexes such as hash index. Hash index is another way of creating indexes for finding data efficiently. Then we have inverted indexes. Inverted indexes are basically for full text search, and hash indexes does not help. Basically, hash index is useful in only exact match. I'll show you examples of how hash indexes work. So how indexes help in retrieving the data faster is that it creates another. Let's say in this big table we have certain tool created which we call index. This small box can be called the index of that table. So this box, basically this area, this tool will help us in scanning the rows efficiently. So, and this box, this index can be balanced trees, can have balanced trees logic, hash logic, inverted index logic, or we will see in vector databases how embeddings are used. So now let us try to understand hash index intuition. Okay, take a hash index. Uh, you take up any value and hash it and jump directly to that bucket. So we can have basically some, let's say we have some fruits names: apple, mango, banana. All right, and we have certain hash functions. This is a hash function. Let's say this is a very simple hash function, and it what it does, it basically takes the word and finds the length of the word and divides it by 4. So length of word, and it takes the modulo by 4, and whatever the remainder is, it put that into a bucket, right? So let's say apple, we have 5, we divide it by 4, modulo is 1, so it goes in, apple goes in bucket 1, right? Now mango also has 5, mango also goes in bucket 1 through this hash function. Banana, it has a length of 6, its modulo is 2, so this will go in a separate bucket, right? This is another bucket. So this is how this hash index work. And if you basically want, if you have a new query, you simply find the hash and you find the bucket where the query belongs. But the trick here, the problem here is, now imagine if I have a new word, apples. We know that apple is there in bucket 1. So we basically want this query to point at bucket 1, right? But if we pass this word through our hash function, what will be the value? The length of this word is 6 modulo 4 2. So we take this to this hash function, and this hash function returns value 2, so it sends it to bucket 2. But we know that apples is nothing but apple. So my point here is, semantically this index fails. So this index is not suitable for our use in AI because it is not giving a semantically correct mapping of the incoming queries. So that's why we need a better index for, or more logical index in terms of generative AI. Similarly, let's say we have another hash function, another index function, inverted index. Now, inverted index, what it does, it takes words and it maps each word to a document. It maps each word to a document, and the matching is performed in a way that each word points to a document which contains the word. So basically, document 1 contains word 1, document 2 contains word 2, and document 3 contains word 3, right? So when a query comes, let's say the query is refund policies. and you want to find out which document should I use for this query, this particular query. So what this index will do? It will match documents. It will match documents which contains two words, refund and policies. It will try to find the documents which are present in which contains these two words, and it will say, okay, I think refund is in document 3 and policy is in policy is in document 2. So it will say, okay, document 2 and document 3 is your document, right? But then if I ask, the query, okay, sorry. But then if I ask a query, money back, but then if I ask a query such as money back rules, so as human, we understand that these two, refund policies and money back rules, these two mean the same. Like semantically, the meaning is same. But this inverted index will try to find where try to find the documents containing money, the documents containing back, and documents containing rule. So it will try to find out the document, and let's say these words are present in some different documents. Let's say these are present in document 1. So this will say, okay, document 1 is your document, but we know that both these queries should have given us the same documents because these two literally mean the same thing. So what happened? So this also fails. So we saw that hash indexes intuition failed, inverted index intuition failed. So now what? So the important thing here is we want some indexing logic so that we are able to map the same meaning queries to the same set of documents or same data. So that is where embeddings enter into the game, right? Now, what is the benefit of embeddings? So embedding solves the biggest problem, solves the meaning problem, semantic meaning. Okay, instead of indexing words, we index meaning of the words. So what we were doing here, we were indexing words, right? But now we do not want to index the word, but rather we want to index the meaning of the word. So the key difference between the above indexing methods and embeddings is that words meaning of words, we transition from words to meaning of words, and that's the development which I wanted to, that's the relation, that's the flow of development which I wanted to show. Okay, now let's try to simply understand what embeddings are in very simple terms. Embeddings are just like a set of numbers, we also call vectors, to show their position or project them in a vector space. To understand embeddings, let's say we have some set of words like refund, policies, money back rules, return process, hate the man, and load the guy. Let's say we have these 5 phrases and we want okay, and let's say we have a 2-dimensional vector space. It's a 2D space, right? Now, if I ask which of these are you want to place the similar meaning phrases together, so you'll say, okay, I would take this and I would place it here. I would take this, I would place it somewhere here. I would take this, I would place it somewhere here. And let's say we have these three dots, this. Okay. Now I would say, what about these two? Now we will take this and place it somewhere here, right? We take this, place it somewhere here, and we say, okay, these two means the same. That's why we are keeping it closer. So to understand this embedding, we see that the similar meaning phrases are sitting together in a vector space. And because these two clusters are not so similar in the meaning, they have some distance. If you try to find the distances, like, okay, one more thing, like we can represent each of these phrases. As I said, embeddings are a set of numbers which we call vectors. We can represent each of them as some numbers which we call vectors, and which will be this number, this vector would be for each of the points, each of the phrases which we have pointed out, projected in this two-dimensional vector space. And if you try to find out the distances between the vectors of these three meanings, the distances will be Euclidean distance or any distance metric that will be very short. But if you try to find the differences between any one of these and any one of this, you'll see that the distance is high. So this is how similar meaning phrases, they stay closer, and different meaning phrases or words, they stay apart. They are projected far in the vector space. So that is the idea behind embeddings. So we are representing each word, each sentences by using a set of numbers. And since it's a two-dimensional space, I'm using two numbers. If it would have been a three-dimensional space, we would use three numbers. If it's 128 dimensional, we would use 128 numbers to represent the meaning of that sentence. Now that we understand the meaning of embeddings, it's time to introduce the final concept here: vector databases. So vector databases is a key analogy here. This vector database is nothing but an index of embeddings, right? It's very important. This is nothing but index for the embeddings. So just like we saw, we had hash index, we had balance trees, we had inverted index, and they were storing words. We have vector databases, and they are the like index of embeddings. So they will store these numbers, these vectors. They create indexes on that, and this is how we use indexes, embeddings as indexes in AI, generative AI applications. There are very famous vector databases, which are, some of them are like Fize, then we have Pinecone, then we have Viviate, and then we have Malverse. So we have these vector databases, and they can be understood as the index for the embeddings, and these are widely used in RAG systems, which is another key concept. We'll understand later how this works in some different video. Augmented generation. And the key idea here is vector databases, they don't store the knowledge, but they store the coordinates. These coordinates they store. And think of embeddings like, if you want to understand this concept in terms of SQL, we can try to think in a SQL way. So basically, instead of when we perform some select query, and when we write where text like refund, for example, um, if you want to write a select star from any table where text like refund. Okay, if you were a SQL engineer, you will write a query something like this. But we can understand vector databases in embeddings, such as in a way that we are writing something like this: select where meaning of the text is approximate equals to meaning of query. So this this is the analogy. This is not exact SQL. This is not a SQL statement I'm writing here, but this is analogy. This is how we are scanning data. We are scanning documents in using indexes like embedding indexes. We have here SQL world, and then we have here embedding world. So if you have in SQL, we have, what do we have? We have indexes. If you have used MySQL or any other SQL server, then you know that we have indexes. In embedding world, we have vector index, we just saw. Then we have, in SQL world, we have rows. In embedding world, we have chunks. We'll understand more about chunks. In SQL world, we have where clause. In embedding world, we have similarity search. So this is the overall idea behind to relate the embedding vector databases with the SQL world. So even the SQL engineers who are watching this video can understand, can relate with how vector databases are, what is the logic behind vector databases. Okay, so why everything, all this embedding world vector database, this matter because in current generation generative AI, we are building many important applications which uses this logic, such as we are building RAG. This also helps us in semantic search. This also helps us in any chatbot which uses documents. This is also important in recommendation engines. So these use cases, vector databases become very important in these use cases when we want to scale it. And we simply, if you take an example of RAG or chatbot which is using RAG, so user basically pass a query, and then this query is basically converted into an embedding using any embedding model, and then this embedding is used to search the most closely related documents from a vector database, and then that fetched document is then provided to the LLM as a context. So basically this the query plus this context, they both together go to the LLM, and then we receive the answer. So if we are not using vector databases, then this query would have directly gone to the LLM and an answer would have been generated. Like this would have been the path. But because we have this new development such as vector databases, we go through this path, and instead of only query, we have query plus this context, right? So they both go into the LLM. So we are augmenting the query with this context, and that is why we have this name, augmented generation, because we are retrieving and then augmenting the query and then passing that to LLM to find the answer. So that's how this thing works internally. Um, yeah, I hope you like it. If you like, then please subscribe to my channel. And if you want this explained using real SQL style examples, or if you want me to build any mini rag systems, just comment, let me know. I will take you through it. Yeah, thank you so much.